pressing the record button. And yeah, that's all. Anubhav, please. The Zoom is yours.
Okay. Thank you, Pavel. I value constructive criticism a lot. That helps me learn. I have glasses, so I learn better when I hear and talk and discuss. So it would be really nice if you could shout on me or say that I'm incorrect or shout between each other, whatever. So, okay. So today I'm gonna speak about something that I started quantum reading or finding out more about quantum theory with, which is the EPR paradox. And today I'm gonna present something that I, with Deva, recently discovered. Um, something, um, something that completes uh, the thing that was started by EPR, followed by Bohm, and then Bell and Coach and Specker and Speckens later. Um, So the first title of this talk is quantum mechanical description of reality is operationally incomplete. So I don't know whether it's incomplete or not, but today I'm going to show you how it's operationally incomplete. I'm going to start with the meaning of operation. An alternative title is my favorite paper ever, which is on Einstein, on the Einstein-Podolsky-Rosen paradox. It's not really about the paradox. I'm not going to speak about the paradox. There is a lot of literature already discussing endlessly this paradox, so it doesn't make sense to talk about it. But I'm going to talk about an operationalist take. What's important here is not my take. I'll try to be as honest to the operationalist take on the entire quantum issue. Okay. So imagine a room in which only quantum event happening is a Stern-Gerlach apparatus right in the middle of the room. So everything else is classical, which I mean by which I mean it's deterministically simulable on some Turing machine. It might be unbounded space, time, whatever tape length. But it's basically unbounded Turing machine, and it could simulate everything that is happening in the room, except for some quantum event. But if you look closer, even in the Stern-Gerlach experiment, we can guess, or we can deterministically compute a lot of details. For instance, depending on the magnetic field, we can non-linear magnetic field, we can completely find out whether how the electron will move at all periods of time in the magnitude of how it will move, but not whether it will go in the up direction or in the down direction. So this one question, whether it will go up or down, something like a coin toss question, is completely unpredictable. It's just not simulable. At least this is what we in quantum information theory believe. Moreover, in a parallel universe, I could just replace this slide with a Mach-Zehnder interferometer, and I could still talk about it, about the quantum phenomenon then, without really referring to the physical substrate. So what is quantum in such experiment for an operationalist does not depend on the particular physical implementation. So he imagines quantum theory in a very minimalistic way, which is some sort of symbol devices, figures like that, like I've drawn here. This is very prevalent in our group. With Marcin, we draw it everywhere. We are such figures. So I have put some little bit of more detail into these figures. Let me get the pointer out. Just a second. Yeah. So you notice that these devices have some shadows underlying them. It's a subtle thing, but these have shadows. So this means that this is on the level where we could operate or we could talk about these devices. What's going on underneath might be nothing going on, or there might be something classical going on, or super deterministic, or crocodiles playing football, or whatever. We don't know about it. So operational is really doesn't care about what's going on underneath the experiment. All he cares about, how do you represent these devices, the preparation and measurement devices, in on your notebooks, like, or in your computer. So, and then a theory, then an operational theory is just an algorithm to use these objects that um, hmm, you use to refer to these devices, prepare and measure devices, to calculate certain statistics, which is conditional probability distributions of the form this, which is some outcome statistics given some preparation P was prepared and some measurement M was applied on it, and there was a readout K. What is the probability of this event occurring? This is what you collect out of the experiment. It's kind of the minimalistic take on quantum theory. In general, any operational theory, and in particular quantum theory, serve a twofold purpose. They predict and they prescribe and they predict. They prescribe objects, in this case, positive semi-definite in quantum theory's case, positive semi-definite operators to preparations, and positive semi-definite operators to measurement. And we have positivity, we have completeness constraints for the measurement, which is they sum up to identity, and we have a trace bound, a unity trace bound on the states. And then you can mathematically calculate what would be the statistics of this experiment, or the relevant statistics for the operation of this experiment, which is referred to as the boundary. Now, this is how I do it on my notebook, and this is how I do it on my machine. And in general, in general, this is how anybody would do it for any operational theory. But the crucial point here is to know that because I'm only looking at computable stuff, so I would be keeping stuff finite throughout this section. Stuff could be generalized to infinite stuff, but for now I'll be finite, but perhaps unbounded. We'll see where those details matter. So what is a realist interpretation of a quantum theory? It ascribes what you refer to as an element of reality, but those of us who do not like philosophy a lot, this could be a classical state of the system. Those of who are quantum theorists, these could be eigenvalues of some diagonal matrix. So, all of this data, whatever this data is represented by this symbol lambda. I think of it as a file, the way it's stored on my machine. It could be stored in whatever way. It could be stored as a bunch of integers or a bunch of real numbers or complex numbers, but it's just a file. And the preparation here represents a probability distributions over these distinct files. So in our computer, everything is enumerable via memory addresses. So mu lambda would be a probability distribution over the memory address. For the classical theorists, this would be a probability distribution over the phase space, and lambda would be a tuple of position and momentum. And in general, for quantum theorist people, this would be diagonal density matrices, where the entries of the density matrices are the probability distribution mu lambda, and lambda is the eigenvalues. And to model a measurement, it's simply a classical readout. So you look at lambda and probabilistically get outcome K. This is the most general treatment of what an element of reality should be.
Can I ask a question?
Could you be a bit more louder?
Can I ask a question? Because you said,
of course, please.
said that for quantum physicists, this lambda would be the eigenvalues, but it's only for one, let's say, operational context.
I said for diagonal matrices, diagonal density matrices.
Okay.
Not all density. This is a trick I'm using. I'm trying to get to the notion of classicality in all languages.
The density matrix of the system, and therefore you always treat it as so lambdas do not exist for pure states. Yes.
Okay, so pure state in density, if in diagonal density matrix space would be just one at the one at one of the diagonal values, no? Just
So
because it's
lambda
we have
is
restricted us.
just one value for pure states.
You could model it in any way. No, in general, for a pure in general, when we want to model operational theory for a pure state, we map it to a probability distribution over lambda and not to lambda. It follows from the fact that quantum theory must not be compared to deterministic theories like Newtonian mechanics, but it should be compared to statistical mechanics like theories like Liouvillean dynamics. Or these are words I'm reading physics at the moment, so but quantum theory needs to be compared to statistical distribution. So in general, pure states are mapped to arbitrary probability. Is it okay?
I don't understand it.
Okay, so could you repeat the question?
Because you said that for quantum physicists, lambdas could be eigenvalues. Now I know that the eigenvalues of a density matrix. Okay, so we have
yes, but diagonal density
lambdas only if let's say if the state is not pure. That's the end.
Mm-hmm.
Okay,
so, here I'm describing general theory. So you could prefer, you could take a theory, a realist theory, and map it to quantum theory. And there are specifications how to do it. But in the context of a finite experiment, finite prepare and measure experiment, I'm not looking at how the entire theory behaves, but just and in the specific context of a finite prepare and measure experiment. So, okay, I'll get back to it later. But for now, you can consider this as classical communication scheme. That's the easiest to talk about. Anyways, it's the same thing. Unbounded classical communication is is almost same to realist interpretation. Anyways, but the realist or the philosophers or whatever ontologists, they can also prescribe and predict, just like quantum theory. So you model a preparation by probability distribution over this realist state or the classical state, and it should sum up to one. So here I've assumed for notation and for my own complete correctness, I've assumed the state space or the ontic state space to be enumerable. So you can sum over it using a formula. But in general, I've not put any bound over the levels of lambda or the distinct levels of lambda. But in general, it could be measurable. And I think I claim that all of what I'm going to show you also holds for measurable spaces. I'll have to talk to good mathematicians to find out. But for now, enumerable spaces. And the response function is just a readout, which is again has positivity and completeness constraint. Positivity means that these are conditional probabilities. You look at lambda and you guess and out and you put an out and you output k. And these describe the probabilities with which you do that. And the probability is sum to one.
Sorry, could you go back to the last slide? On the bottom line, you have a summation over this response function. It shouldn't be the other.
Yeah,
yes, it's just a typo. Okay.
Yeah. Yeah, you're right. Okay.
No, I just wanted
Yeah.
to check if. Mhm.
Yes, yes, yes. This is the right one. Good. Thank you. Thank you so much. Okay. So files and on computers and stuff. And these you could make predictions, and predictions are just basically summing over your ignorance over your classical state, averaging your response function over the ignorance of your ignorance of the classical state. So this is how you get statistics. Just like the bond rule, you can do it here. These are two levels. Till now and throughout this stuff, I will not bound Hilbert space dimension or the dimension of the ontic space at all. So that's important. So, yeah. So ICDQT's latest favorite realist interpretation is what I refer to as the row-ontic interpretation. It basically follows from our belief that only the ensemble is real, or only the ensemble can completely describe physics, or something like that. Ensembles super important. Pure states are not that important. Pure states are looking at pure states as real causes a lot of problems. But if you take ensembles, you could be safe. You don't have to call quantum theory non-local or something like that. You can just, or non-contextual. You can
What do you
just.
mean by an ensemble? In that moment?
Could you be a bit more louder? Sorry.
Could you define what you mean by an ensemble? Now you are talking about it, and I don't understand fully because you don't have.
Okay, so here technically what I mean, what really exists is just a row. Okay, think about the universe as a classical, deterministic, very powerful computer. So what will it take in input to produce the probability? It will take the density matrix as it is written on your notebooks and on my PC. This is the mathematical version. I can discuss. We have to still make. I have to still create the incomplete physical viewpoint of the interpretation. But here, what I mean is a computational realist interpretation, which is a mathematical interpretation. So just a second, I draw it properly, and this is the drawing is attributed to Deva, uh, and next to a brains. So here you have mu lambda, and here you have some distribution, and the state space, the state space, ontic state space is equal to some oral space over Hilbert, and row one, row two, row three.
Okay, so you mean ensemble of the hidden variables, okay?
Yes.
Okay, because
Okay.
okay, I thought that you think about the ensemble of equivalent preparations.
No, not any of that. Nothing of that. Row ontic.
I want to understand every word of your talk.
Yep. Okay. Okay. So okay. So I refer to this as the computationally real interpretation because it understands how difficult it is for my computer to do the SDPs that I type on it, like very freely. So it basically presupposes that that uh, maybe you find a good algorithm to get the bond rule, or maybe just replace the bond rule with simple. But if you are, it will always be as hard as doing it on a deterministic Turing machine. Like if you have these density matrices, then as the necessary description of your physical system, then you will have to compute it, uh, and you compute it on a deterministic Turing machine. Then churning the bond rule will be as hard as. Okay, this is a bit. So this is a bit something that I need to talk to complexity theorists to get to. But in general, this is how the interpretation is defined. So for any state in of any Hilbert space, there is a separate distribution. This is the only thing real. There could be more details to it that we don't know, but everything is separated. So it's a very rudimentary interpretation. It also kills imagination. So you're not imagining atoms or molecules anymore. You're imagining basically a file that stores the entries of the density matrix in a memory location on a computer, which is our universe, or at least we are assuming that to be for enumerable. Okay. Okay, but operationalists do not like to talk about reality. So they must come up with operational properties of certain kinds of devices. Here we are interested in devices that emit weird stuff out. Like we don't know what it is, question mark represents that. So the device emits some weirds about quantum, whatever, some stuff is coming out of there. But we define an operational property of such devices as some properties that are statistically independent of the allowed set of measurement devices. In this particular seminar, I will speak about properties that can be operationally falsified. For instance, here SO is basically a generic property. This is which is the guessing probability, maximum guessing probability of certain function of the finite number of settings of the preparation device. So if I will assume this to be the property of this device with X inputs. So there is a device with some labels as inputs, and you can distinguish those inputs with some probability, a maximum probability SO, or distinguish some function over that input with maximum probability SO. Now, if this is incorrect, then you can show it to me. This is very important because this is called operational falsifier. So if SO is greater than what I'm claiming it to be, then you can show it to me. Otherwise, it is not operational. Okay. So this is completely theory independent structure. It's a number. It's a probability. It's a measure. It's not a probability. I have intentionally kept this unnormalized here, but it's a metric, and it's a randomized metric. So if you can do better, you can show it to me, and then I'll change this number accordingly. Okay, so in quantum theory, this is just such properties from semi-definite programs. And the answer for any given set of quantum states or density matrices, the semi-definite program, because of the Slater's theorem, yields optimal values to up to machine precision. But it's good to remember it's a semi-definite program. Is everybody okay with this? Why is it a semi-definite program? Because it's a maximization is over all POVM measurements, and the number of outcomes of this POVM is equal to the number of or equal to the range of the function fx. So it's over that space, all such POVMs, and POVMs are basically positive decompositions of identity. So it forms a semi-definite program. Okay. Okay. Now for the realist, you can also evaluate such properties, which is just now consider this. Here there is no bound on the Hilbert space dimension. We don't know what D is, and similarly here we don't know what lambda is, and so these problems are difficult. But in general, for any finite number, this is a linear program. So we have a general stuff on probabilities, then a semi-definite program, and a linear program for calculating the same metric. Okay. Which is maximizing over all realist measurements. So this is independent of what you can do. So it does not depend on the set of measurements allowed in your operational theory. It is okay. So it is on the ontic level. I'll come back to this. This will be important. Okay. So let us see. So the metric associated with guessing a function f of x is simply given by this equation. It is maximizing basically probability of k equals f of x given x over, so you're just maximizing this probability here. Okay, so you can actually solve this for the functional gains, and you can also solve it for all linear functions over probability. So in general, for any communication complexity, it's very easy to solve this. So to solve it, notice that we could write this equation as we could just spread it out, which is for each lambda, it's the sum of mu1 lambda times so this is x here, so you're enumerating, you can just write it this way. Now the set of response functions are only constrained by positivity and completeness. So for any finite lambda, or no, not even for finite, for any finite outcome, they form a convex polytope. Convex polytopes are very nice stuff. And this is a linear functional over the convex polytope of the response schemes. This is a set of and this is the set of all response schemes. Lambda. And so you can just for any three given realist states, you can just evaluate this functional over the extremal points. What it amounts to in terms of classical communication is that you look at lambda, and then you output the x or you output the x for which so you output the value of the function f of x, which has the maximum probability of occurrence. So that this is what is written here in math. So for each lambda, you output the particular x, which has you output the particular value of the function here. Sorry, this is here. A value of the function which has the maximum probability weight. This is just some mathematical details. We'll come back to it. Now, this is how I define completeness of an operational theory. So I define very general class of operationally falsifiable properties. If they are incorrect, you can tell me and I'll update my worldview. Okay, there is nothing. This is so I define an operationally complete theory as an operational theory which provides a complete description of reality. If for all such operational properties of devices, there exists a realist explanation or a model which prescribes probability distributions and response and readout functions, such that there is an explanation for these values. That's what operationally complete theories are. At least this is what I think Einstein is doing justice to Einstein's in an operationalist worldview. Anyways, this is something that we introduced together with Deva in our recent, but this is building up on that. So this is not contained within that manuscript. This is for the first time I'm actually writing it down. It was in my notebook. So it might be all misplaced. So please help me out. This is also a generalization of a very cool thing going on in foundations, which is called which is a unifying principle, which unifies all these notions of classicality. It's called the no fine tuning principle. And Matthew Leaf and Lorenzo Catani have a recent paper on it. It's also a generalization to that. This is how I define completeness. Okay. And this is what I will prove. that quantum theory prescribes sets of preparations for which there exists no realist interpretation, such that all operational properties have a realist explanation. And I will just show it for three properties. Well, that's counting properties would be different, but this is what I mean by incompleteness of quantum theory.
Sorry, what do you mean by operational property of S?
This. Uh, where did it go? Just a second. Oh. Yes. This is for quantum. This is operational. Yes. So this is just a success probability, maximum success probability of guessing a value of some function of the input of values. You maximize over all measurement. So this is not dependent on your measurement. For any operational theory, this is just the property of the preparation. There is a divide in quantum theory. You have states and independent measurements. So whenever there is such a divide in those theories, you can, and in all theories, you can do this. Is it okay? Why is it a property of just preparation? Okay. So I'll show that quantum theory is not complete. And this would be like, okay, less to Einstein, more to Bohm, but still I decided on Einstein for this slide. This is for me a correct way of resolving the values. The properties that I'll take are very easy. I'll take a metric for distinguishability, which is just an unnormalized probability of guessing what is X, and you maximize overall measurement. So this is all for given sets of preparations. I'm talking about operational properties. This is a distinction that will come handy later when we talk about communication. But for now, for any three given preparation, distinguishability is a measure of how well you can tell them apart. So there is a ability in the word distinguishability. Ability is how well I can do or how well we could do. So that's why I refer to this as distinguishability. Okay. Distinctness has the connotation of something to do with actuality, independent. So I call it, I just call it, I use this term to define the realist counterpart of distinguishing, which is just the distinguishing probability of a function of just the label of the setting of the preparation device. It's just the maximum distinguishing probability. Okay, but we can use our trick and solve it and get a very succinct expression, which is just responding with the label X, which is just the success probability when you respond with the label X. So which has the largest probability of occurrence. Okay, let me show it to you. Maybe graphically it would be better. Okay. This device is new to me, so excuse me. Okay. Suppose you have two quantum states, 1, 2, and some probability measurement, and you have some probability distribution like this. So here I am, or you have some space of quantum states and two preparations. Sorry, this is a real space, so just lambda. And the then the realist probability would be taking the max person for all of these points and integrating the surface underneath. So you lose in the overlap. So you are always losing at least for one preparation in the overlap. Is it most people are familiar with this, but are you? Is it okay with them?
Honestly, I don't understand what you mean by losing the overlap.
So okay, let me zoom in a bit. So in the overlap, So for a same lambda appears for 1 and 2, okay? This one lambda here, this appears as a result of preparing preparation 1 and preparation 2. These are probability distributions that are, sorry, mu1 lambda, this one, and mu2 lambda. So when you sample a lambda from these probability distribution, each lambda that occurs here in the overlap region occurs occurs from both preparations.
Yes, so you mean that you cannot distinguish then, yes?
Yes, so in one round, if I say that this comes, if I decide to say that this comes from one, I will lose in the other, in that particular round. It could have come from the other, even on a real level, okay? Is it okay? Okay. Now we have established language, and language is good. So I will define 2 more properties. This is very easy. This is total pairwise distinguishability. So I'm only considering 3 preparations. So they could be represented on a triangle. This will come in handy as well. And this is some kind of a distance measure of the edges of the triangle. So pairwise means you take 2 preparations at a time. Just do not touch the third device or third setting at all. Just take 2 preparations and find out how well you can distinguish them. So total pairwise, okay? You can define the ontological counterpart, just plugging stuff in, I hope properly, but this works. For now, yeah, let's move on. I think I missed this new property. It's not in the BOD paper, so it's new. So it's anti-distinctness. It's important. It's the anti-guessing probability. So you have to output, the game is that you output what is not X. So you output, you can either output, so if X is 1, in one case, you can win by outputting 2 and win by outputting 3 in both cases. So I call it anti-distinguishability. It's because this also forms a function. There is nothing new here. So, and the ontological counterpart is called anti-distinctness. I'll come back to these structures. You'll see them more properly in the proof that follows, which is pretty easy. Okay. So I will now derive a statistical inequality, a statistical equality only based on operationally falsifiable properties for all operationally complete theories. This in this lemma. So for any complete operational theory, and for any 3 given preparations in that theory, this equality holds. So what is the equality? The maximum, the maximum total pairwise distinguishability is equal to distinguishability plus anti-distinguishability. Okay, this holds irrespective of the particular theory, or if it is complete, then it holds irrespective of the type of preparation. It holds for all 3 preparation sets of a theory. Okay, this is what a completeness argument should look like in the end on the operational, because it's complete. You have a communication task on this side and communication task on this side. This is what I mean by completeness. I will formalize this. It has a very nice mathematical formulation in terms of, but we will talk about it. Okay, let's go over the proof. The proof was very hard initially when me and Deba 2 years ago we did it. We made sets of 3 probability distribution, looked at each possible overlap, and it was a total mess. But recently, I found out in a book, it's called A First Course in Probability. So I'm not, this is a book, it's called First Course in Probability. So now, but this proof is much more general, not just for probability measures. It holds for real numbers. this is where this might come in handy for generalization and later. But for now, for any three real numbers, if you take the maximum of pairwise maximum, it's always equal to the total maximum or three maximum and the maximum of um, two sums. Okay, I can't put everything is in English, but it's okay. Let me write it out because there are just three numbers, so I can write it. So max over mu naught, oh sorry, mu one, mu two, plus max over mu two, mu three, taking on mu mu one, mu two, mu two, mu three, and then mu one, mu three. And this is here, and this side can be written as max over just mu1, mu2, mu3 plus, okay, I'm not gonna write it out, right? Okay, maybe I will write it out. So this is mu1 plus mu2, it's inside the bracket summation. So it's not maximum. Oh, again, this is too bad. mu1 plus mu3 and then mu1, 2, 1, 3, 2, 3. And the well, you don't really need a proof for this, but still it's elementary. You can consider an associated ordered list. So for any arbitrary set of three real numbers, you can have an associated ordered list. I call it ABC. Then you can see that both sides of this above equation yield the same number 2AB, 2A plus B. So it trivially holds for all real numbers. In general, it holds for any ordered stuff, not just for real numbers, but for now, real numbers is enough. We are already beyond probabilities. This is important for some stuff, anyways. So now I'll do an ancient technique. I'll just sum over lambda. So whatever was holding earlier. So this would also hold for probability measures. Here I will take real measures, but also for probability measures mu lambda. So, and you can sum over this lambda, and what you get after that is just the properties that we had defined. This total pairwise distinguishability, well, anti-distinguishable, like anti-radial. Okay. Good. So this completes the first half of the proof that this holds for any realist interpretation. Now, completeness argument helps us to port it to the operational level. That's what the completeness argument is doing mathematically. So we get to our lemma that this should hold. Okay. Is it okay? Because now there is nothing left to do. Oh, why did this up? I had some animations. Yeah. Okay. But anyway, so we will consider these three states. These are colloquially referred to as Mercedes Wednesdays. These, for some randomness project, Martin introduced me to them, and I found them really nice. And also, it's in this particular. This is a official video of a song which is linked in the acknowledgement of the quantum paper, and it's also there. And it could be the local temporal reason why I looked at this stage in the beginning. I happened to randomly look at it. So we'll take these three states. We are all familiar with them. They are on the Bloch sphere. So this is a Bloch sphere representation. And on the real plane of the Bloch sphere, there are three states. They are separated apart with 120 degrees each. So very, very symmetric stuff. Okay, so SDP calculations. So you get some so if you take the total pairwise distinguishability, so you're maximizing out over all possible projected, all possible measurements, POVMs or projected, whatever, using an SDP, and the computer and me, we both come up with the same answer. Actually, this is, you don't need to use a computer program. This is just trace distance, because this is just two preparations. For two quantum preparations, this guy is just trace distance. I do not remember how to write it. Some distance and trace. Summation over all ij. So this would something like that, or a function of this. And this is the number that you get. And distinguish with this is this is, so you can see if these are qubit states. So this would be less than equal to summation over x m over k x, and I think because this is less than equal to all of them are less than equal to identity, then this would be less than equal to 2 by 3 r. Okay, there is a way to prove this without even looking at the machine or solving this optimization just by taking dimension assumption. I can't come up with it at the moment. It's not that important. Just a number 2 and anti-distinguishability. So these are just, so the best POVM that distinguishes these three Mercedes-Benz states is just the Mercedes POVM. The POVM that anti-distinguishes is just the Mercedes POVM, anti-Mercedes POVM, or something like that. So we have, for any complete theories, these three properties must be the same. And for quantum theory, this is not the case. Okay. And this is a measure on quantum theory's incompleteness, an experimentally verifiable measure on quantum theory's incompleteness. It's a fact. You can't do better than this. If I make these Mercedes preparations, you cannot distinguish them more than these values. And if you could, you'd show it to me. And if you could do only just that, then this is the measure of quantum theory's incompleteness to realistic. Incompleteness in the realist. It's a tiny bam moment. Okay, so now I look at what this stuff should be compared to. We have some notions of classicality, all good notions of classicality, if they are to be treated as notions of reality. In that case, their dimension, we should not restrict the dimension. Also, this has about 12 gigs of quantum memory, which is 12 gigs of classical dimension, which is crazy amount. Classical dimension is crazy. Quantum classical comparison over dimension. So these are the notions of classicality BOD should be compared with. So not dimension, but we can check dimension later. When we come to classical communication, dimension is super important, and then we will check that. But anyways, my favorite is, of course, Bell stuff, because it relies, it gives you the onus of justifying your operational assumption, which is no signaling to relativity. So as quantum theorists, we don't need to care where no signaling comes from some other theory. But it is composed of two separate assumptions, which is locality, the assumption of locality, which is just pushing no signaling down on the lambda level. This might be a cashback to last year's similar time presentation, pushing down. So when you push down no signaling on the lambda level, you have what you call a parameter independence or locality. But then Bell makes this extra non-verifiable auxiliary assumption, which is even violated on the quantum level. If by the rho-ontic principle, which is by the rho-ontic model, which is outcome independence. Oh, but it's just there. So it was justified earlier for people to feel uncomfortable with saying that quantum theory is with the statement that quantum theory is non-local. They would make us say quantum theory is Bell non-local. And I agree with that. That is correct because there is this extra assumption which is even operationally already violated if you take the quantum state to be the hidden variable. This is super weird. Similar, but very on a on a different level, there is something new that I really, really like. It follows from Leibnizian principle, though it's all messed up at the moment. I need to figure it out properly. But it's called generalized non-contextual. Simply speaking, it says that two objects that cannot be distinguished ever by me or humanity or machines, humanity combined, must be represented by the same ontic. We must have the same ontic description in general. But this is not violated by quantum theory. What is violated is a conjunction of Leibnizianity and a scrambling principle called convexity. So this is good assumption when you're looking at classical communication models because they are all convex, the states there are convex. But when you talk about reality, you have to not make any assumptions that are operationally justified. Otherwise, the Copenhagenist would say, oh, there's nothing weird about quantum. But what I've just shown to you is there is no escape from it at all. Quantum theory, in the sense that I've shown to you, is incomplete. I have made no non-verifiable auxiliary assumptions, only operationally falsifiable assumptions. Okay, so this is with my, this is what this result should be. Hello?
Okay, so is it the end of the seminar, Anubhav?
No, I'll have 2 minutes more.
2 minutes.
2 to 10 minutes.
Okay.
10 minutes.
Maybe I'll just say that if anyone has some questions now, and if they want to leave, then maybe we can have a pause for questions.
Yeah.
I have a question. I'm challenging, so let's say, your wording. Because what
that is up for grabs. So help me write it better.
What you are showing is completeness, not incompleteness. Because if you say that a complete theory must have those ontological lambdas which form some kind of distribution or whatever, then obviously the quantum mechanics is incomplete. But Einstein-Podolsky-Rosen were thinking just oppositely, that the formalism of quantum mechanics.
Okay, this has to be debated. I have not been talking to a lot of people who are interested in this segment. I've been talking to mostly mathematicians around. So this is my point of view, and it's from my reading of it, and it might be incorrect. We should continue discussing this. But for now, this is.
But the thing is that, let's say that the title of your seminar is, let's say, kind of gives an obvious association with the title of Einstein-Podolsky-Rosen paper. And,
it is for colloquial.
They meant just.
I've not decided on the. Okay, but okay, you say it's the opposite. Could you explain it to me in a very in an easy way? Like because I'll discuss with you further.
I say no. Now I'm thinking that perhaps you, yes. But
okay, let's roll along with it for now.
I perhaps if I can, last sentence, it could be formulated. Can we complete?
The complete means exist. This stuff for me, complete means existence in a determinist on a tape on a deterministic Turing machine that is churning out my universe. If it is beyond that, it has implications that are very important to me.
And the other thing is, of course, I disagree with you that outcome independence is something strange. For me, it's just a consequence of Einstein's
Sure,
causality.
Einstein was only looking at EPR pairs. That's why we call them EPR pairs. You don't call the Mercedes-Benz states EPR states. It's I'm not referring to the particular paradox they posted. I'm talking about the general feeling that they had, or at least a vague implication that they have of incompleteness of quantum theory. And this entire presentation is not my point of view. It's an operationalist, true or purist operationalist point of view, how to deal with that question,
Yeah,
or at least a part of that question.
Now
Okay.
let's say I almost agree with you, almost, but this is disputable.
Yeah, it's important. That's why it's almost addictive to work on this, and I can't stop talking about this because this has more implications. This inequality that I've showed you can be arbitrarily generalized for n levels. I worked on it for 1 day with Levy and Oscary from in hell. I'll talk about this quickly. I'll just finish everything up because there is some regulation stuff I need to show you. In our So this is what we have done. So we have one interpretation, rho-ontic interpretation, takes the quantum state, makes it the figure of, makes it element of reality. This survives Bell non-locality. There is no non-locality here, just outcome determinism. No signal, there is no signaling on the lambda level, even because of Bell violation. What's going off is outcome independence. Of course, I remember that this is only true for finite alphabet experiments. If you are allowed infinite alphabet experiments, there is Kolbeck-Renner stuff that can only prove violation from parameter independence. But I'm talking about finite experiments because I don't think nobody can do infinite continuous variable settings ever in time. This is also how my computer.
You claim that you cannot have continuous settings?
No, but at some point when you record the data, it would be from one setting, and only in finite amount of time you only be able to get finitely enumerable settings. This is my favorite part of the implication, which is very recent, which is there was this rho-ontic interpretation, because of which I was not allowed to write well non-local or quantum theory is non-local, which is correct. I think that is correct. Also, quantum theory is non-contextual in the most general sense. And if you leave outcome determinism, you get Cauchy-Specker non-contextuality as well. So everything holds fine when you take this. It holds fine because it's computable on my machine. And my machine is non-contextual, and my machine is local causal. That is why it holds, and nothing is weird with rho-ontic interpretation. But even any realist explanation whatsoever must be incomplete in this sense. We have made no assumptions about composition of the system, so no parameter independence outcome determinant. It applies to super determinism as well. And we have made no assumptions on the convexity of the state. So there is no structure assumed about the theory at all. So when I'm making such claims, what I find back is that there is no return to classicality. This is where my understanding stops. Now I am just explorer. But what defines quantum theory? So there is no, this island is away from home, but we don't know what rules this island. So that I'm working on with other people. But in our group, we say whatever we work on must have quantum advantage. Otherwise, at least that's the minimal requirement. I'm on the border of the minimal requirement, but anyways. So you can think of these, whatever I've told you, as a game. The game is as a communication task. So now I'm not talking about for any three giving preparation. I'm talking about channel constraints. Now I'll put channel constraints here about distinguishability plus anti-distinguishability. I'll just put a constraint, I just less than equal to P. Then the Mercedes-Benz states violate this clearly, as you can see. It what happens here is that you can take the ontic description because I took the enumerable set. This is also D dash classical in general, but it happens to be the same as two-dimensional. So this condition, so this oh, sorry, I just so this okay, this happens when you shift from many operating systems. But anyways, so this such constraint is sufficient, can sufficiently capture the dimension constraint, as we shall see in a second. But anyways, when you give a complete notion of classicality, what do you expect? I expect such things. You reduce in, so here you have the quantum and classical stuff on the y-axis and your channel assumption on the x-axis. The classical stuff forms on this. This is a projection of the probability space that could be formed from these two broad class of theories, unbounded classical and unbounded quantum. This is a projection. The classical stuff forms a line, which is a one-dimensional object. The dimension of the spaces of probabilities out of unbounded classical and unbounded quantum stuff, they differ. So you get almost 100% quantum advantage. Whatever qubit, 3-qubit stage that you sample, you will have quantum advantage. And yeah, that's what should happen if you are completely strictly operational at all level and you're giving a definition of completeness. You shouldn't get inequalities like Bell inequalities or quotient or contextual inequalities. You should get equalities. It's a matter of completeness. This also says this, a corollary of this, that all communication complexity is really only dependent on upper bounds on all other communication complexity. It's not dependent on, say, the dimension assumption, which is later related to communication complexity, or no signaling that induces some kind of structure in communication. It's really dependent on other communication complexity. So a communication complexity stuff can be converted, maximizing one communication complexity can be is constrained by maximum amount of some other communication complexity. This could be proved. This is proved in previous paper. Anyways, all the references that I have been contained in these two papers, I call this the egg paper. Okay. So egg paper and the heart paper, and these have a lot of details in it. I still have to, we have to, with the further, we'll have to process the heart paper a little bit more. But it's very nice. I really like it. And I almost died, and we almost died writing it. And this other paper has been published in quantum. So see, this year I had to do all of this mostly on this particular stream that I'm following on my own. But this was all there in our colloquial friendly discussions in Chick with Deva, and in general discussions in 102 and other rooms. Also, the first time that I found it after found this kind of thing that it started bothering me, I presented in Hell. And then Oscar and Levy, they helped me to get some generalized definition for n number of preparations, which that's why I have not put it up here. I need to contact them. Also, this new perspective on the same on this result is because of ongoing continuous discussions regarding this topic with ontology, with Paolo, Goran, my co-authors, Mate, Vicky, John, and Marcin Pawlowski. And I was funded by a first team grant earlier, which is no longer, and now I'm currently funded by Sheng. And this is my bike. I'm going back to it on 12. And that's and on the right side, that's an album that I recently discovered, and it's eating my brain. It's very nice. It's just amazing. Thank you so much.
That was my favorite album when I was a teenager.
Well, okay, that Billet, it's one of my favorites. I really like it. It has this song Epitaph, which is my favorite of the movie.
Thank you very much, Anubhav. Are there more questions or comments? Marcus, maybe you have a question?
Yeah, I have a very basic question. At which point do you exclude that the variable lambda is just a density matrix? Kind of in your model. Since you do not put any bound on the space for lambda, why not just using the density matrix as your variable lambda, and for your conditional probabilities, you are just implementing the Born rule?
Exactly. That is what my machine does, and this is what this interpretation that I introduced in this.
But why will you be able to beat if you just apply the mathematical rules of quantum mechanics in your classical model? Why do you still see a discrepancy between the two models?
Yes, because the set of yes, this is very, very interesting. Okay, I have not completely. This was bothering me up till 30 minutes ago, so it might be incorrect. So I'm in deep waters if it is incorrect. So I'll try to explain what I found out up till now. Where is that graph? Okay, yeah, here. So suppose I take any of this point. Okay, for this point, these are only distinguishable by this much probability, whatever that is. But in quantum, you can get average pairwise up till this point. For this average pairwise thing to have a realist explanation, it should have a much higher success probability. Somewhere, I don't know, here maybe. 5.
No,
yes,
how do you calculate, how do you arrive at those numbers other than by the Born rule?
Just by averaging out. This is by this proof, this maximization minimization proof. It follows from something that is called maximum minimums identity. It's
no, and I'm really pointing at this fundamental question. If I'm just using the mathematical rules of quantum mechanics, if I replace lambda by my density matrix, if I replace your conditional probabilities psi by the Born rule, then I should get, using this model, and I don't see at which point you forbid that, I should be able to make the very prediction you get for quantum mechanics. So to me, there's a fundamental problem.
I see what you do. Yes, I understand. So there is one, what you're doing is a GPT theoretic treatment, which is like you take the entire probability vector and make that a state. Yes. So this is something, so this is what I'm discovering. This is if that GPT, these conditional probabilities, okay, it's related to joint measurability. Okay, I had to discuss all of this with my other friends first, but I can speak about it. I'm not sure if,
No, I don't want to make that discussion now with everyone, but as a strong kind of recommendation, that's to me a very important point that should be addressed in any talk.
Okay, I will address it now.
Yeah. Since I have another question for you, and then maybe we can take it offline at some point. Sure. When you have the pairwise thing, in that definition, you have an ion and a J. But I don't really understand at that point, kind of in the operational picture where you have the two preparations labeled with I and J, whether you're sending two states and make a joint measurement, whether you're sending a single state or what's
In
What's
which
really going
image?
on
Are you
here?
talking about communication game?
Yeah,
Thingy or
so
what?
stop. You had this box where you have, you're inputting a set ij.
Just a second. Just a second. Let me find that out. Where is that? Yeah, is this it? Yeah, tell me.
Yes. Do you have a measurement ij and you have
Yes.
the xij, and the question is whether you're just having one state, you're having two states.
No, the question is okay. Is the question is guess the index of so if the state is x is indexed by x is indexed by I, then guess I. If it's indexed by j, then guess j. It's just for any given pair labeled by say cats and dogs, then the measurement output has to be cats or dogs. That's all. So it doesn't matter what symbol goes into ij, it's just the same symbol should appear here. It's semantic, so it could be generalized to
So you kind of, you split your problem into many problems where you are promised that it's either I or j.
Yes, exactly. Oh yes, you're right. You're right. So the communication task that is the equivalent is a promised communication task. You're right. You can get a smaller communication complexity, but today was simplicity and elegance. There is a smaller game possible with just two measurements, which is the smallest communication complexity, and with three inputs. Yeah. Okay. Yeah. There was that game. Oh yes. Okay. This is the game. So there is a promise that x will only appear, y will never appear. Say y would not be, x would not be 3 when y is 1 to be. And so there is this kind of a promise in this task. But this task is up to me, so this is still operationally verifiable. It's not an adversarial scenario, it's me. Is it? This is a very interesting question, and it has been bothering me. The other question, I do not know. I have hints about what's going on. The idea is this is something like something like Fine's theorem. So you cannot so all ontic stuff could be written as a big a big measurement that reveals the ontic state. And all other measurements are post-processing of that particular measurement, or it's called the God measurement or whatever. And everything is. So this is like, so this notion of completeness is equal, I think it's equal to joint measurability. But that I'm not an expert of. I have some PhD student ramblings at the back of the notebook that I would love to explore. This would be very nice to explore. So yeah, that's it.
Another partially related comment is when you impose that something is discrete enumerable, at the same point or with the same argument, I think you cannot speak about probabilities. You have to go to frequencies.
Oh man, I do not cross that. I have crossed that road colloquially, but I'm waiting for graduating first.
So in the end, you will have to introduce some epsilon, since it was the true probabilities.
Okay. So because of the sake of brevity, I also, and because it's a declaration, I also have this experiment is not to be done like a communication complexity experiment. It has to be done as you go into the lab and you randomly.
On the high level, is that when you oppose to having continuous things, then you cannot talk about probabilities. Then you're only performing finitely many experiments, and what you have is some frequencies.
Yes, but both the realist interpretation and the quantum theory, I am so the testing ground is experiment and probabilities. This is what the testing ground is, but this is finite. All of these stuff that I've assumed for the mathematical theories or the algorithms, I think they could be, or I claim, or I should talk to mathematicians, could be generalized to infinite stuff as well, measurable spaces, whatnot. Like, but the experimental thing, what these algorithms will be used to predict, the probability is there, they are finite.
No, it's not probabilities. It's frequencies.
Yes, it is frequencies, but the theories output probabilities, and these are tested up to some epsilon in terms of frequencies. But the thing is, if you prepare these Mercedes-Benz stage, you get like, I don't know, all sigmas of deviation. So zero detection efficiency, because there zero detection or very low detection efficiency is required because the dimension of the classical space and quantum space is different. Unbounded classical and quantum stuff, that is different. So you do not, this would be very easy to show violation. What I was planning to do with Mohammed and people in Sweden, I proposed to them, I don't know how seriously they took me, is to walk inside the lab and just prepare random states and violate with the dimension assumption in place and tomography completeness, and do tomography and stuff like that. Then I have some experimental robustness calculations as well that you might want to check out later. So it is experimentally very nice also, it's not bad, but it would be an experimental random sampling or some kind of boasting of quantum theory's power. Okay. I can't.
Any more questions? If no, then thank you, Anubhav, again. There is no seminar next week because of national holiday, so see you in 2 weeks. Thank you, everyone, for attending. Bye.
So just one thing, if you have questions,
stay healthy, and remember that it's a dangerous period, okay?
Psychologically sane.
It's really...
The anchors take green.
The situation is very grave. Best of luck.
Bye-bye.
Bye. I will just wait for a minute.
Anubhav, do you want to add something?
No, if anybody has questions, would like to discuss, I am actually almost helplessly thinking about this. So
maybe I'll stop recording now because I have to go. Maybe I will make you the chair of the session.
Please,
okay.
Yes.
And then you can continue.